Okay, we're going to do another video on integration. I think this is one of the very last topics. Actually, it might be the last one for specialist maths. Yep, this is the last one. Solids of revolution. So now we're going to be looking at, so we've looked at area under the curve and area between two functions. And now we're going to use this trick where we're actually going to work out an area formed by a function that is rotated around an axis. So consider this. Consider the volume formed when the area between the function f of x, this one I've drawn in red, and the x-axis from A to B is rotated around the x-axis through 2 pi. So in other words, you take this function and you imagine it swinging it all the way around the x-axis. Okay, the method how you do that is you find the definite integral, or pi times the definite integral, of the function squared dx, or y squared dx. And we use y because we're actually going to be doing this along the y-axis as well. So imagine we have like something like this kind of parabolic shape. And we swing that around the y-axis. Well, in a similar kind of way, whoops, don't forget the pi. I might just squeeze it in there. There we go. I forgot my pi. So when you do it with the y-axis though, okay, it'll be x squared dy. And the definite integral go from c to d instead of a to b, where c and d are the corresponding y values of a and b. So thereby f of a is c, f of b is d. That's important. Okay. Now, you can look at the examples yourself on, all right, this is the last question I wanted to do, so let's maybe just go back to the start of this topic. In the textbook, they do a pretty good job of showing why these functions work in terms of they kind of build them up out of cylinders, and that's kind of explains how this method works. All right. They also have numeric examples, but for my examples, I actually wanted to go through and do some, we can actually show some formulas. So I did, for example, volume of a sphere from a semicircle. So if you draw a semicircle across, I actually made a mistake with this. I realized what I did wrong. Let's see if I can zoom this in a bit more. And then I went and corrected it. Get that a little bit crisper. There we go. All right. So a semicircle, you could use the function of, because if you're swinging this this semicircle around the x-axis, you could use the top of the circle because the bottom gets represented as you swing it around. So y equals square root of r squared minus x squared. All right. Now, when I did this the first time, it kept collapsing to 0, so I changed it so it was only the from 0 to r, but I decided, okay, I found my mistake, so I corrected it. That's why I see so much white out there. All right, but this is the method I've gone and used. Okay, y squared. So square that, you get rid of the square root. So pi from minus r. So this is a general circle, general formula for the volume of a sphere. Is what I'm trying to achieve here. Okay, integrate that, and then apply the boundary conditions. Simplifying this statement, you end up with 4 pi on 3r cubed. So, yep, that's one way you can come out with the formula for the volume of a sphere. All right, so let's try another one. And this example, I did the volume of a cone from a line. So imagine I just draw a line from the top of the cone to the base of the cone. So I called my y value here h, and my x value there r, whereas the h is the height of the cone and r is the radius. If I swing that around the y-axis this time, I can actually come up with the formula of a cone. So First of all, I came up with an equation of a line in terms of y, just by working out slope. So you go across r and down h. So slope is minus h and r, and I just came up with there's the equation of a line. However, when you're if you're rotating on the y-axis, you need to write your functions as statements of x, which is counterintuitive because actually that I think I can contradict myself with what I've taught before. Functions can't always isolate in terms of x, but okay, we're writing a x is the dependent variable and y is the independent variable of our statement here. So rearranging this, you can write it, well, linear lines you can. X equals r minus r on hy. But when you're doing rotations around dy, your statement for x wouldn't even have to be a function because there's a bunch of statements you can isolate x for, which wouldn't satisfy the vertical line test. And you could rotate those around the y-axis, I imagine, without any problem. Okay, the volume pi. All right, so remember when you're rotating around the y-axis, you have to go make sure you're using the boundaries of the y. So we are going from 0 to h and rotating this thing around, yes. Okay, all right, if you integrate that in terms of y, which I've done here, simplify, I made another mistake. Oh no, that was just me crossing out all the zeros that come in when I substitute. And you end up with the formula 1/3 pi r squared h. Again, the volume of the cylinder. The cone. All right, volumes of two defining functions is the other thing we're going to look at. So instead of just filling up the whole volume surrounding the axes, we can actually draw shapes that may have regions which the volume is not counted. So a torus, for example, we also know that as a donut, is such an object. So if imagine I've got this circle here, I can go and rotate that circle around the x-axis and form a donut. However, it's a little bit more tricky than that. If I try to just do that, well, one, I can't because I can't isolate that as a function. A circle as a function. I can isolate as two functions. See, I've drawn two functions, one in red, one in blue. Okay. Now, if I was to rotate the red one around, well, basically what I would end up with, in particular, if I did it for that set domain there, I would end up with something. Yeah, well, your donut would be filled in basically, and it would actually have a region of flat on the side. But if I work this out in terms of two functions, in this case, I've got an upper function and I've got a lower function. They are the red and the blue functions. And again, I've decided to go and try to find a general formula. So I actually did look up the formula for a torus, and I designed my problem here to overcome that. So you imagine one form of the torus I looked up had variables of the capital R, which was the distance from the center to the center of the donut to the middle of the volume. So you see that R goes up to the middle of this circle, and then you have a smaller radius, which is this R here, which makes up the circle. So in terms of that, I was able to come up with a definition. Now, there is actually a problem like this in the book. However, it is not. There actually is no questions in the book where you have to go write general formulas. So I'm just doing this for a bit of fun. It wasn't so much fun though, because this one is very hard and a lot of research. But I'll show you the question where you are dealing with torus, and they do help you out a lot. And you are working at a volume, not a general formula. So this is me trying to set it up. Okay, volume pi from minus r to r, integrate of the upper minus lower functions squared. Don't forget to square the functions. And this is a lot more complicated than I actually thought initially. So I went and I had to do a little bit of research. I tried one way, which I'm not going to show you because it's actually outside the scope of the course. And actually, you can do it by, although it's very difficult, you can do it by integration by parts. However, I had to go look it up and I tested for myself. So I showed that this was equal to that, and with that, I was actually able to integrate what I had left. All right. So hence 4 pi r. Okay, so this is what I actually want to integrate this point. This is the reduced integral after I've done expansion and cancellation. Okay, and I ended up with the correct formula in the end, but I'm not going to go any further with that because it's actually beyond the scope of what you need to do. But as you can see how cool this thing is, it's actually you can come up and you can check all your different formulas. So let's actually move into the more of the problems you'll be looking at. So we're going to take a few of these questions. So from page 118, let's look at question 1. So we're going to start off by doing everything around the x-axis to start off with. All right. So the volume of the solid formed, the body is resolved around 2 pi on the x-axis. So I'm going to pick 1f. So 1f y equals. All right, so this one looks like you are actually, this is actually the top of the circle, but this is not going to be a torus because you don't have the lower function, so you're not having the donut hole in your donut. All right, so let's integrate this. So the integral would be y squared dx from 0 to 5. Well, no, sorry, this is actually a sphere because actually it's going across the whole thing, not just part of it. All right. Okay. Yeah, because you're going from, I can see that. All right, so let's just go and substitute this in. So 0 to 5 of y squared will actually be 25 minus x squared dx. All right, and that's equal to 25. Oopsies, I keep forgetting the pi. There we go. Don't forget your pi. All right, integrate that. Minus 1/3 x cubed. 0 to 5. All right. So pi equals pi 25, 125 minus 1/3 of 5 cubed. And that will be minus 25 times 0 minus 1/3 of 0 cubed. All right. Get my calculator. I do have a calculator program up, but I'm just going to go to the one in front of me. Actually, that would be a plus, but it doesn't matter because it's 0. Just trying to make it more correct. All right. Okay. It's actually 250 on 3 pi. All right, whoopsies. Nope, I do have it in the correct position. There we go. All right. All right, and there we go. So moving on. Okay, so next one you got to use technology. So there's no actual program in the graphing section that can really do volumes. So we're just going to use other things here. So let's have a look. Let's go into our integrals. No, that one. Okay. Now I'm wondering if I can actually insert a pi in there. Oops, I got rid of it. That's unfortunate. All right, well, let's start off with a pi first. Let's put our pi in first. Okay, and then we'll add the math integral. So math 9, there we go. All right, so this one, all right. So for question 3b, actually, sorry, I haven't even loaded up the question yet. Let's remember that there was one I had to do on the calculator. All right. Yeah, we're finding this one. So from 0 to 360, yeah, you're just using the formula for pi. So in other words, we're trying to find this. Okay, pi squared, pi of function squared from 0 to 2 of, now instead of just doing it with the calculator, I'm just going to not bother reducing it or anything like that, and just put squared and dx. Right, and that's it. All right, so let's go work this out on the calculator. 0, 2 of, I'm going to put another bracket in there. Of sine variable, bracket squared, and dx. Okay, let's see how we go. All right, that is our value. That's probably the easiest way just to go and evaluate these ones. So rounded to 30.2. And that's it. That's all we're going to do. Okay, so let's move on to some other ones. All right, so for these ones, we're actually going around the y-axis. And just a reminder that the y-axis ones, all right, pi theta d, where they're the y values, x squared dy. So there, and when you integrate, you're going to be integrating with statements in terms of y only. All right, which is going to mean that we're going to have to find inverse functions. Which is all fine for you guys because you've had loads of practice with that. Let's start off with the first one. All right, so if y is equal to ln x, x is equal to e to the power of y. So they're inverse functions of each other. Okay, fair enough. And then we can actually go and, okay, well then x squared equals e to the y squared, which is e to the, by your laws of indices, multiplied powers. That's the easiest way to go about it, I imagine. Okay, so then we can actually substitute in the integral. All right, so integral is equal to, so the volume is equal to from, other thing I have to work out. We want to find this from 0 to 2. So the boundaries is 0 to 2. All right. Oh no, sorry, they're not x values. Oh, we don't have to do any conversions. I was just worried there for a minute because it said I thought it said x equals 0 to 2. No, you don't have to do that. That actually comes up in part E though. You notice here actually some of them actually it's D and E. You do have to convert the x values into y values. C you do not. So that's all right. So yeah, it's this boundary conditions of 0 to 2. That's no problem at all. All right. Okay, find the volume. All right, 0 to 2 of, okay, well, we'll substitute that straight in. So e to the 2y dy, all right, equals pi 0 to 2 of, all right, integral that's e to the 2y times by a half. All right, and let's just go and evaluate this. It'll be 4 minus 1/2 e to the 2 times 0 and the pi there. Okay, And simplifying that, okay, so you got e to the 4. So I'm going to write it this way. Pi on 2 e to the 4 minus, now this will collapse to be 1 times a half minus pi on 2. Okay, so that's an exact value form for that. And that's a kind of question they might like to do in the exam to make sure that you know what you're doing by expressing them in terms of unknown transcendental numbers. Okay, so let's move on. What question do we got now? 10f is the next one I picked. Let's have a look at 10f. All right, so now we're moving into, oh no, we're not. Pretty sure that's there. Yes. Okay. All right, so this one, okay, again, we're going around the, actually, we're going around the x-axis. Oh, okay. Yeah, we're back to going around the x-axis. So we've done a y-axis one. All right, so this is just this revision of some of your trig skills. All right, so pi, I'm just going to jump into it. Pi of tan x, tan squared x plus 2. Okay. Dx. Now, nifty thing about that is I could write it as, okay, sec squared x on 2 minus 1. And I forgot my boundary conditions. 0 to 2 pi. I'm sorry, pi on 2. Okay. All right. All right, the sec squared is actually 10. Sorry. Put that down. All right, start off with pi bracket tan x. Oh, sorry. Let's just go first things first. No, I think I was right. What I was doing. Oh yeah. No, I know. Sorry. Still on holiday mode. Okay, so integrating this. It's actually 2. Yeah, because if I differentiate, the half comes out the front and becomes sec squared. Yep, there we go. And let's evaluate that from 0 to pi on 2. And then that would be equal to tan pi on 4. Yeah, 2 tan pi on 4. 2 tan. Let's put a pi up front. Minus 2 tan 0 on 2 plus 0. All right, simplify this. Pi out the front. Tan of pi on 4, 1 on root 2. Well, times by 2 would just be root 2. Minus pi on 2. And that goes to 0, and so does that. All right, so there you go. If you want to expand that out a bit more, root 2 times pi minus pi squared on 2, I think. Try it for yourself. I think I might have even, just going to quickly check. I had a feeling I did something. Nope, no, I did that right. Yep, no worries. I had a feeling I was about to write a half in front of there. I thought I did that somewhere else. No, that was actually, there was a 2y and in the e function, and I brought down a half. Okay, so that's the reverse. All right, so let's move on to the next section. So this is now volume of 2 defining functions. So in terms of, yeah, I'm trying to make a torus. I'm trying to get the volume of the torus. We have to cut this up into 2 functions. One is the positive answer for well, the circle can be expressed as well, in this case it would be x takes 0, sorry x squared, yeah, x squared, and then bracket y take 3 squared, because it's been displaced up 3. Y take, well, bracket y take 3 bracket squared, equals the radius, and the radius appears to be 1 unit, or radius squared, I should say, which is also 1. If you rearrange that, you have a statement that goes y equals 1 take x, well, I should say actually y minus 3 squared equals 1 take x squared. And then when you undo the square, you can end up with plus or minus. And then the top half of the semicircle is the positive result, and the bottom half is the negative result. All right, but you don't have to do a torus until question 6, which I will be doing in a minute. All right. But in general sense, you can do this sort of work where you have an object that may have some sort of hole in it where the volume doesn't count. All right. All right. So let's do this question here, question 2. Find the shaded region of involved around the x-axis. All right, so the general function around the x-axis is y squared upper minus y squared lower dx. All right. Okay, so I'm just going to substitute these in. And the boundary conditions, all right, first of all, we need to find, so that's from A to B. Right, so we need to work out an upper function and a lower function and our boundary conditions before we move on. So we start off by finding the coordinates of A, like it's asked us to do. All right, coordinates of A, okay. E equals e to the x, x on 2. All right, just use natural log. 1 equals x on 2, x equals 2. All right. So, and we need the coordinate. So the coordinate is also, well, the coordinate is that 2 in E. But we don't need the y value. So this integral becomes 0 to 2 of the top function over this domain is E, so E squared. And then we have minus E x on 2 squared dx. Simplify that into 0 to 2 E squared minus E to the x dx. All right, now this is quite simple because that's just treated as a constant. So for the sake of the integral, oh, and of course, I keep forgetting my pi's. Let's put your pi. Don't forget your pi's. Pi, bracket, e to the 2x minus e to the x from 0 to 2 equals pi 2e squared minus e squared minus 0, and so e squared times 0, that's gone, and then plus e to the 0. So pi e squared minus 1. That'll do. Okay, so let's skip through some of these because they're all just applications. I think this is probably the more challenging one because this is actually, this is not a function, this is a relation. It can be separated into 2 functions though. It's important when you're writing in terms of the rotating around the x-axis. I haven't seen a question where this is such a thing has been done, like you've made a donut lay flat on the on the or in the middle of the x-axis by rotating it around y. That would be a different beast as well. You have to write statements in terms of two functions in terms of x with the variable of y, which is again counterintuitive because of the way we define functions in these courses. All right. All right. So we got this is the equation of a circle. And the circle is going to be rotated around the x-axis in order to make a torus or donut. All right, so we're going to isolate, try to isolate y for the purposes of that. All right, so x squared plus y minus 3 squared equals 4. All right, so show that. All right, show that. Okay, yep. All right, so move the x across. So y minus 3 squared equals 4. Take x squared. Y minus 3 equals plus or minus the square root of 4 minus x squared. And then just move that across. Y equals 3 plus or minus 4 take x squared. Okay, so we've shown that. That's what asked us to do in the first part. Illustrate what part of the circle is represented by that. Okay, so basically, this is that is your y upper equals 3 plus root 4 minus x squared. And this part is the lower. Sorry. Okay. All right. Find the volume of the torus by revolving the shaded region through to pi. And they give you a hint. So I think I do this in the general sense by integration by parts, but we'll see how we go. So that's E, that's C. So let's go find this torus. Don't forget your pi. All right. So area y upper squared minus y squared lower dx from what would be our boundary? Oh, let's just write A and B for now. Our boundary conditions in terms of x. All right, so you can see here we've got 0, move across. Now this has a radius of, okay. Oh, sorry, that's 3. So 3, yeah, this has a radius of 2, and you can tell by that if you remember your function. So if you move across, it's minus 2 to positive 2. All right, so minus 2 to positive 2 of, let's work this out. All right, area upper, so we've got 3 squared, got my pi, 4 minus x squared. And minus 3 minus these are all squared dx. All right. So yes, this is going to be a bit messy, but we'll give it a go. Okay. Minus 2 to 2. All right, so we're expanding these parts. So expand them as you would imagine. You use FOIL. So plus 6 root 4 minus x squared plus 4 minus x squared. I might just put that into a bracket. Minus 9 minus 6 root 4 minus x squared and plus 4 minus x squared. Now, thankfully, after that, this reduces quite nicely to a point, which is a little bit difficult to integrate, though. So that's subtracted. That is gone. But these add up. So I'm actually going to bring the 6 and the 6. You actually end up with 12. I'm going to put that right out the front. 12 pi, because why not? Because 6 plus 6. Yeah, minus minus plus. dx from minus 2 to 2. Okay, so that's what we're trying to integrate. Now, we don't actually have an integral for that on our list. However, we're going to use the substitution here. X equals, which actually makes sense because that substitution is going to, we can use some raw rules actually for that. Lottie's in the way I was attempting it before. All right. When I wrote the general case. All right, so now, if, I might just write a statement, if x equals sine u, and I might just work out the root of that, du by dx actually. I think I'm working this out backwards. Okay. Du by dx. So I want to integrate in terms of u. I have to actually write that as the inverse. Well, that actually complicates things. Oh boy. Okay, I hadn't thought of that. I have to write this in terms of arcsine. I have to go back to my arcsine rules, which I didn't use arcsine much in the last iteration of this course. All right. So yeah, but basically, if I want to work out du by dx, which is what I want, because I want to make this integral in terms of du, I have to write this as u equals arcsine x. All right. So then du by dx, I'm running out of space, so u equals arc sine x equals or do I even have to do that? So use a substitution. Okay. Do I have to integrate in terms of u? I think, okay. I don't think maybe I don't have to do this. So let's just skip that for now. So I should have practiced this one beforehand. All right. I'm going to do the substitution, and I'm just going to carry the variable u, and then see if I can change it. All right. The purpose is, okay, I'm going to end up with sine square. Actually, sorry, it's 2. We've got the 2. This is how it works. Okay, I'm going to do this on the next page. All right, so I said there was 12 pi from minus 2 to 2 square root of 4 minus 4 sine squared x. So that's how this is going to work. We're going to end up using identity. So sine u dx. Okay, so this actually can be expressed as, all right, so take out the 4. Which again, you can actually take out that 4 entirely like that. So 1 minus sine squared x dx. I might even take that out the front. We just keep gathering more and more stuff out the front. Square root of is u, not x. All right, so we get cosine u. All right. Unfortunately, this statement was x equals sine u. So at least we got something reduced now. Not exactly what we wanted. But at this stage, if I think of it, turn this into okay. The problem is the reason why I was looking at stopping this. All right. Reason why I was sort of stopping that one is I can't evaluate the boundary conditions because arc sine of -2 to 2, unless I got that wrong, is the x value. Yeah, it's got a radius of yeah, it seems to be a bit of a pickle because that does have a radius of -2 to 2, and I don't know what to do about that in terms of if I was to convert these x boundary conditions into u boundary conditions. Well, arc sine doesn't like that. It only likes to be defined between -1 and 1. So I don't know what to do about that, to be honest. Oh no, that's the reason why. Ah, because I keep running it like that. I keep running it without the 2. Of course you can evaluate that because it's actually, well, in that case, it's all right, you got to divide by 2 first. It's arc sine of 2x. Of course you can. All right, well, I suppose, all right, I'll go finish it off then. That was my mistake, and I'm sure someone watching this is just screaming out what my mistake was. All right, arc sine of 2x. Now, if you want to write it, u equals arc sine. Let's just fit this into which I'll write underneath. U equals arc sine of x divided by 1/2, because that's the kind of format that we've been working in before. And that would mean that we have 1 over 1/2 squared minus x squared. Okay, and also the boundary conditions. Well, all right, so if x equals -1/2, u, so -2, u equals, well, it's arc sine of -1, which is minus pi on 2, and x equals 2 is u equals, that's when arc sine of 1, which is pi on 2. Okay, so those boundary conditions. So we can actually change this now into a definite integral that is still going to be painful. All right, so this is a tricky question. All the same. All right, so cosine u times 1 on 1/2 minus squared du by dx, and that cancels the dx's. And then we've got integral purely in terms of u with the correct boundary conditions. There we go. That's what we want. However, oh boy, now it's not quite looking like something we would like to do. However, let's just remind ourselves of the integration by parts. Now, I might just double check my integration by parts. Okay, uv dash dx equals uv all right. Not sure if that would actually help either. Oh, of course, actually, I haven't actually gone and done the sine goes into there as well. Does that actually help? Double check I've got this part right. Arc side of that seems to be about right. Okay, that's one. Yeah. Oh yeah, because I can't actually. No, I can't actually integrate that. I still got an X in it. What am I talking about? I have to go put the U back into it. And let's just do one more reduction. I think I've got a strategy here that's going to work. All right, so this. Okay, I should have actually had a look at this one first. So that's all right. Let's just have a simple substitution for us to do. Oh, sorry, that's a u and that's a du. I keep mixing up my terms. All right, so let's just run it this way. Actually, this looks okay. This looks doable. Yeah. Or is it? All right. Ho hum. Okay. So, I mean, if I did this in terms of so we've already had one subject. I keep doing it. There we go. All right, I'm gonna have a look. I'm giving up, but this video is going to come too long. People are just going to get bored. So let's just go have a quick look at this one. I think all right. 2 questions 6. I'm going to quick look at the word solutions, see if I'm actually on track. Yeah, I mean, there's that. Okay, I've reduced it to that. Yep, that's what I did. Then, hold on. dx by du cosine u. But how's it end up being a du? The whole reason you do du by dx is cancelled. I don't understand how that works. I don't think so. So dx by du equals cosine u. That makes sense. Okay. Oh, I see. Yeah. So they've actually done. Yeah. Okay. It did upside down. Yes, that actually does make sense because if you you've got to change the dx into dx by du. Okay. That was actually all right. So that's okay. So I made too much work for myself trying to do as the du by dx. All right. Maybe even I'll just go back to this step here. So 4 sine u. So I'll go to my 24. Zero to 2 of, I'll go to this, sorry, minus 2. I'll go from cosine u dx, and I'll write dx over du equals 2 cosine u. Yeah. Blah, 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 then I can use my boundary conditions that I worked out before. They're fine. Oh, are they? When x equals 0, u equals 0. No, they're not. 0 to, if I use the arc sign, x equals 2. Yeah, all right, fair enough. Oh, they got boundary conditions of 0. Oh, they're doubling it at the end. No, they doubled it beforehand. That's why I got 48. So they've only gone from 0 to there and they doubled it? Okay. Yeah, okay. I see what they've done. Yeah. As in, there's a even function symmetry, but they didn't actually use that. No, I'm still right if I got 24. So maybe I'll stick with my method. No, actually, this is easier. 48 pi, 0 to pi on 2. So I'm going to go with that because that's going to be easy to evaluate. Then cosine u. So the idea is then dx equals 2 cosine u du. So then 2 cosine u du. Where did my 2 come from? I think actually, oh no, I'm not meant to be 48 yet. the 48 comes after we do this part. Mine got doubled because of something else I brought out of that. That's how it got at 24 when I was doing this stuff. Right, 2 cosine u, cosine squared u du. No, actually, I think that's right. No, that's right. No, that was right. Sorry, 48. All right. So using some of the double angle formulas, 1 plus cosine 2u du, and here's how you do it. Okay, so I mean you can follow on the rest of it here. So yeah, this is the first case I've actually had to use dx by du, but just be aware. So that didn't pop into my head. So that was the main problem. I kept thinking I had to isolate for u and find du by dx, but I didn't. So this also works as well. So then you can write, you can just replace by doing dx by du, you can just replace the dx with 2 cosine x du, and that's how they went about doing this. All right, so with that fixed, and that's the final solution, I'll leave it there. So you can see this one's actually a little bit tricky and put some outside thought into it. So even though I went and did the Taurus for the general case, yeah, and this is not simple by any means. All right, I'll leave the video there. Okay, so have a go for yourself.